Hi and welcome everyone to the last day of the Pint of Science Festival in Trondheim. I'm really happy to see you all joining us here, and also welcome to the people who is joining us online from wherever they are in the world. But Pint of Science is not only happening in Trondheim. The other way. Okay. Pint of Science is a worldwide festival that is taking place in 25 countries around the world. It's entirely run by volunteers, and our goal is to bring science out of the lab to the pub and to have some fun learning about what the local scientists are working on. So in Norway, you can find Pint of Science in 6 cities, including in Svalbard, which I personally find really cool. And as you can see, it was created in 2012, and it grew really, really fast. And now we have numbers from 2019, where we had 24 countries, and actually we are 25 countries doing the festival this year. So usually every day is around a topic. And here we can see some pictures from the festival in 2019 in Paris, in the top left, in Mexico City, in the top right, in Russia. And this year we are especially lucky because most of the festivals are happening online, and we in Trondheim have the chance to have this hybrid event and welcome you all at Habitat Pub, and also welcome the people joining us online. So what it is for the speakers, this is an opportunity to put yourself into the spotlight and to present about your work to a completely different audience that you are used to, that doesn't necessarily know much about it beforehand, and to maybe get then some unexpected questions. And for the public, it's an opportunity to learn something new and to have some fun together while enjoying a pint and learning something new about science. Thank you so much to our sponsors, and also to Dion for sponsoring the event in Trondheim, and especially also to Habitat Bar for hosting us. Welcome everyone, and my name is Alicia, and with Anne-Claire, I'm going to be presenting tonight.
Thank you so much. Yeah, so welcome everyone. So this is our third day. So for those of you who were not here during the previous days, day one we talked a bit about COVID and about things that are not so obvious, so some things that you might not hear about in the news every day. Then yesterday we went into the nano world, so we talked about things that are really small. And today we're going to talk a bit about space. Now space is obviously super exciting. There's a lot of interesting research going on that's, well, in the media. But space has probably fascinated humans for, well, since we first started walking around on the planet, just looking up at the stars, wondering what's up there. We wanted to understand and see what's up there. We built telescopes. We wanted to put people up there. And now we got to a point where, as with all the places that we explored, we want to get resources from there. We want to mine things in space. We leave a lot of rubbish in space. And we want to now do commercial flights to space. So today we're going to talk a bit about, well, some things about space flight, but also about things in space, such as planets and stars. And I've got a lot of respect for our three speakers, because a lot of these concepts that they're about to present are really not easy to simplify, or at least I get the impression it's very hard to simplify. But I suggest that even though the topics might be quite hard to understand, I'm very confident that they'll be able to communicate it in a very efficient way. But pay attention, because at the end of the evening, we'll have a Kahoot quiz, which is basically a quiz that doesn't just test the accuracy of your answers, but also the speed. So pay attention, and the winner for tonight will receive a 250 kroner gift card from Trondheim. So yeah, definitely worth listening to what we're about to say, or what's about to happen. So then for tonight, our first speaker is Michael Kachelries, who is a professor at the Department of Physics and he's an astrophysicist. So astrophysicists, they are physicists and they apply the rules of physics to understand the things that happen in space, like stars and galaxies and how it all forms. And there's a lot of difficult concepts that I've never heard of that were in your CV that I can't even try to explain briefly. So, well, on your Insta, when you're entering a new page, I'm sorry. So he's going to talk to us tonight about antimatter. I knew what matter was, but no idea about antimatter. So really looking forward to giving you the floor. I'll just disinfect the mic. Can we have a warm welcome for Michael?
So thanks a lot. I don't know if I managed to, the expectations are high and now I have to fulfill them. So antimatter. So let's start. As every normal person nowadays, if you know nothing, you take the internet, Google, and then you see antimatter. One thing I found, this antimatter t-shirt in yellow, you can order for 230 crowns. So it's not very expensive, just white, many different colors and so on. The more traditional way is probably that you start from a history, quite some kind of a historical approach. And so first, to understand what's antimatter, maybe good to recall what is matter, right? So let's say matter, as our Greek colleagues said, well, we should look for the very small things. And so you could think about the elementary particles which constitute matter. And so the first particle which was really discovered was the electron in 1897 by Thomson. And then it took a while to figure out that the nucleus is actually something relatively compact. And then Rutherford, say 19 or 20, really figured out that he could kick out of the nucleus a proton, and he could then discover this proton. And later on, then there was the neutron discovered in 32. And out of these three particles, now you can essentially build up everything, the tables, the Earth, etc. Right? You can have now this kind of picture where you have a nucleus constituting out of proton and neutrons, and then electrons flying around. And it's a naive picture, but it's not so bad. And out of this, you can now explain the periodic table of elements, understand chemistry, and obviously then if you understand chemistry, you can build up, as I said, a human, the Earth, the stars. And all of the stuff is now constituted out of these three building blocks, and this is matter. Right, so this was 32, and at that time already people looked in cosmic rays. This is energetic particles which come from outer space, hit the atmosphere, produce new particles, and this was at the time when you had no accelerators, men built a kind of way to look for high energy phenomena. And so one of these guys was Anderson, and what he built was a bubble chamber. So essentially this is a chamber where you evacuate. So there's a low pressure and there's a water pressure. So if a charged particle moves through, you can see the track. So that's essentially the track of a charged particle. And then you add the second ingredient, the magnetic field. And that's the nice thing, that the magnetic field, maybe I have not enough hands, but maybe you remember this right-hand rule from school. You have a kind of current, and then you have a magnetic field, and this gives you then now the direction of the force. And then you see, well, depending on the force, the direction is either the curvature is turned to the left or to the right. And this allows you now to distinguish the charge of the particle. And then you can now see, well, a positron, a particle with a positive charge would have a curve like this, an electron like this. So this guy discovered a new particle. And it has essentially all the properties of an electron. It has the same mass, but it has the opposite charge. Right? So you have the same mass, but the opposite charge. And later on, other particles, antiparticles, were discovered. So essentially, you have for each particle the corresponding antiparticle. Right. And now this obviously now raises the question, our guy in the anti-t-shirt, maybe it was an anti-human, it was an anti-t-shirt, and the guy was living in an anti-Earth, in an anti-solar system, in an anti-galaxy. Right, so just looking at this thing, since photons, essentially they don't distinguish between an electron and positron. So this picture, we could not distinguish by looking at this picture if the guy is a guy or an anti-guy. Right, so no way, just by looking and using photons, electromagnetic radiation, to distinguish between matter or antimatter. And that's obviously now the question. Well, we know we are made out of matter, but what about the rest of the universe? Right, so let's look a little bit deeper. So one famous formula from special relativity. Okay, normally you know this in the form, how is it? E is equal to mc squared. Right, so this, you can convert energy and mass, and this is the formula valid for a particle at rest. But if you have a particle which is moving, has a certain momentum, then actually these are two contributions. This rest mass, and then on top you have the kinetic energy, like you could think the non-relativistic particle is 1/2 mv squared, the kinetic energy. And this means essentially now that you can interchange momentum into mass. Right? That's the way how in a modern accelerator you create new particles. You take light particles, you accelerate it to very high energies, and then you just collide them, and then you can create new stuff. And that's, for example, one example here. You could take photons, which are just energy. You take two photons, they collide, and then if you look this in the way that time increases to the right, then your two photons in initial state create an electron and a positron, so a particle and an antiparticle. But you could look also in a different way. You could look from the right to the left. Then our matter and our antimatter particle, they meet, annihilate, and create just energy. Right? And this is the kind of thing that we cannot have the situation that in the first picture there's just an anti-t-shirt and the guy is a normal guy, because then it would just explode. Right? So we need essentially a kind of separation of domains where there's only matter and there's only antimatter. Otherwise, the typical thing will be that your matter just annihilates and produces radiation. Good. Now, if you look in more detail into this kind of reactions, then you realize that there are some conservation laws. So one thing which is familiar to you is electric charge is conserved. Right? So you see here in this example, you start on the left, the photons are neutral, so the electric charge, you sum over the charges Q. On the left-hand side, it's 0. And this means now the sum over charges on the right-hand side, it's +1, -1, 0. Right? So you can create electric charges only in pairs, plus and minus 1. And there are more conservation laws. There's one if you would like to create now this protons and neutrons, which are the building blocks of this matter. There are now antiprotons and antineutrons. And you could think charge conservation, electric charge conservation, would allow you to create a neutron and maybe two neutrons only, right? They have 0 charge, so you could create an arbitrary number. But there's an additional conserved quantity, that's you could think the nucleon number. And so you can create only a nucleon and an antinucleon. Technically it's called a baryon, and then it's a baryon and antibaryon, but it's the same thing. So you can create only matter plus antimatter, such that the difference of matter minus antimatter particles is always the same. So the relative difference is conserved. So if the universe at some point was electrically neutral, it will stay electrically neutral, and if we have a zero, the same number of nucleons and the same number of anti-nucleons, then it will remain forever like this in this simple picture. Yes, so now I allow myself the freedom to have one slide which is a bit more technical. And this is just because I'm a theoretical physicist, so we could take this for granted. Or there are guys who observe, they see there's antimatter. So let's try to understand why there should be antimatter, why there has to be antimatter. Right, so that's the point that if you combine special relativity and quantum theory, then if we are clever enough, then we can predict that there's antimatter. So if you look first, the old Newtonian view of space and time, then these are two different things. Space is one thing, time is one thing. And then if you take, for example, some point, then it should make no difference how we choose our coordinate system, for example. But it should not make a difference if I put my coordinate system here or there, or if I rotate the axis and so on. So the physics should be always the same. And on the other hand, time is not affected at all by changing space. The only thing by which I can time change is I can change the origin of time. I can take a different calendar, the whatever, Christian calendar or some Mohammedanian calendar, but all the physics is the same. Now we come to special relativity. Okay, there's some equations. And 1908, Minkowski realized that there's a nice geometrical interpretation out of this. So now we cannot just say there's space and there's time, but actually there's space-time. So the two things are unified. And you see now we have an axis time, an axis for the space. And if we take now the unit such that we take, for example, 1 year, which is 1, and then we take a light year, then the light just moves along 45 degrees in this diagram. So this means that this thing is essentially the light emitted from one point, and this would be the signal which we receive from the past. So very nice. And now we can think about the important point, the time order of events. Right, so in classical physics, this is a very nice feature. You are born before you die, but this makes life somehow straightforward. And how do we see this? That we have our time axis. The constant times are parallels to the x-axis. So we have some events, and then we could say B happens before A, because if you would now take the second parallel, it is before the other line. Right, time increases from below to the top. Now, this we have to take for granted. Now we have this mixing transformations which mix space and time, and these transformations which are equivalent to rotations only in space. If you do the same thing in space-time, then the effect is the following. That actually it's not like I rotate both axes by the same angle, for example, to the left, but I rotate them together. So this means that the angle is now smaller. And now we can look again at this diagram. So for our new system, the times of constant time are still parallel to x, but x prime. And now you see that the order is different. So now it's not anymore that we have B was before A, but B is after A. Right? So this is the kind of main thing that in special relativity now, there is not an absolute time order in some regions of space-time. Right? So now this creates this a problem. I mean, you could think now, if you have two observers and one sees first somebody dying and then is wrong. This is a problem. And the answer is no. So just to have this thing, okay, we have two observers. One sees that the particle is emitted at B and absorbed at A. And for the other one, it's the opposite. So what is the resolution for this problem? You could think this is a particle which carries a charge, and then the current, this is essentially the charge times the velocity, and the current is the thing which enters all the physics. So the current has to be the same for the two observers. Let's just write. So this is the charge, and the velocity is just the distance we travel divided by the time. And so let's assume that this is positive for one observer. And now for the second observer, is that the time is always changed. So I get here a minus sign. And this means that this minus sign has to be compensated by the charge. So this guy sees the particle, or his interpretation is that the charge of the particle is the opposite. And this means not just that O sees a particle, O prime sees an antiparticle, and therefore to be consistent, we need particles and antiparticles. Moreover, this tells you that that you can really exchange them. They should have the same mass, but they should have opposite charges. And so that's the famous interpretation of Stückelberg and Feynman, that you could think an antiparticle is like a particle which travels backward in time. But it's a little bit too sloppy, but it works for many interpretations. So actually, I don't know how much time do I have. It's okay. Okay, so now we come back to observations. So we saw that if we have matter and antimatter, the stuff will annihilate. And so the question is actually, what are the domains on which we could have only matter or only antimatter? And so the first thing is you could ask the solar system, and then it's obvious, if we can go to the Mars or Moon and the moon mover doesn't explode, then this means the moon is existing only of matter. Or you could also just think the solar system, there was some original soup, everything was mixed, and from this you form the sun and then the planets. So since it was mixed, everything has to be matter. Then you can go on and you look for the Milky Way, our galaxy. And so that's a picture of the Milky Way taken in gamma rays. So these are these photons with high energy, which would be produced if our electrons and positrons or protons and antiprotons would annihilate. And this is now the picture. You see here the galactic disk, and that's essentially the region where you have many of these high energy photons. And this stuff just comes from astrophysics, which we understand. There are sources which accelerate particles to high energies, and they explain this kind of emission. But the stuff from our antimatter annihilation, it should be also at high galactic latitudes. And so you could just look there, and there is essentially nothing which we would expect if there are this kind of annihilations. But in the same way, now you can go, this is now our own galaxy. If you think about different galaxies, then there would be some overlap in between in the interstellar medium. Again, you would expect there's some kind of gamma ray background, which is created by these annihilations, which the universe would then act just a kind of calorimeter where all this energy is accumulated, and it's not there. So this means you can repeat this for galaxies, for cluster of galaxies, up to the largest scales, and there's nothing from this annihilation photons, which indicates that all the observable universe is actually consisting of matter, right? I'm not sure. So how much time do I have?
Yes, 15 minutes left.
Good. So 1 minute. Just so cosmology. You could have another argument. Again, just theory, which tells you all the universe has to be only matter or only antimatter. But that's essentially that. Probably have heard about this Big Bang universe, which is not really the last up-to-date of the pictures. So the idea is that there was a period where there was a kind of very fast expansion of the universe. And this means that after this expansion, it was an enormous factor, something like 10 to 50, and there was essentially afterwards nothing there. So even if God was there, he created somehow some asymmetry, matter, antimatter. Then unfortunately this period destroyed all these initial conditions. Then afterwards there's nothing left. And this means you have to create matter or antimatter or asymmetry dynamically. So this means you have to put in some physical laws to get out the stuff. And they tell you that essentially on even much larger scales than what we observe, you expect only matter or only antimatter. Right. Good. So now I'm an experimentalist and I don't believe this stupid stuff of the theorists. We just have to find things. And so if I'm a very prominent experimentalist, then I can convince funding agencies that they spend money for an experiment which is somehow guaranteed to find nothing. And this is called the alpha magnetic spectrometer here, there. So that's again a big magnet that you can distinguish the charge of the particles. And they try to find antimatter. You know, even if it tells them there is nothing, they try, right? And so this is the head of the collaboration, Nobel Prize winner, Samuel Ting. And here is a conference, well, a colloquium at CERN, where he announces that they have anti-helium-3 and anti-helium-4 detected. And so this is, you see, for example, here they measure the momentum, the charge, it's 2 plus minus something. The mass is consistent with 4. And so they are present this at least as an evidence for anti-helium-4 nuclei created in or found in our own galaxy. And I'm really sorry that I'm very late, but you could think that antiprotons, light nuclei, are created in circumstances like in our accelerator. You know, the galaxy works in some sense also like an accelerator. But Jonas is working very hard to calculate the probability how likely it is that you have anti-helium-3 or anti-helium-4, and the answer is that you will never find anti-helium-4 except there are really anti-stars, and there's the nucleosynthesis going on in the stars. So final slide. What does this mean? So if this observation of anti-helium-4, which is not published, it's just announced at colloquia and so on, when they need money from the funding agencies. So if it is true, then you could say this is a revolution in cosmology, because obviously I told you in the standard picture you should not see it. This would require that there are really some anti-stars in our own galaxy. Right. Or obviously something is wrong with the experiment, which is always the easiest interpretation. The guys just don't understand the errors of the experiment, and that's the reason why they never published a solid paper, but they just give this kind of talks as I do it here. Right. Good, thanks. Thanks a lot. Sorry for being...
Yeah? Try it now.
Yeah, working? Now it's working.
Yeah.
Thank you so much for your talk, Michael. That was incredibly complicated, but very interesting. I have a lot of questions, but I'm sure the audience has some questions as well. Or if they don't, I'm happy to start with one. So you say that the first evidence for this antimatter was that they found electrons that basically have a different charge. So they first found the anti-electrons, so to say, right?
Historically, it was the first, yeah.
So then you have antiprotons, but what about the neutrons? Because they don't have a charge. So how do
So
they?
this
Is there an
what I-
anti-neutron?
What I tried to tell you that this is this kind of anti-nuclear number. So there's not just electric charge, the conservation of electric charge, but just you look out and already the fact that essentially everything which is that there's no conservation law should decay to something lighter. So why the proton exists, it doesn't decay in a positron, for example, because there's a conservation law which keeps the number of nucleons constant. And this is essentially the neutron has a nuclear number 1, and the proton has also nuclear number 1. And so I'd have to create a neutron and an anti-neutron. So you could think in more detail that these particles, they are not really elementary particles, but they consist of 3 quarks. And in one case, you have 1/3 plus 2/3, you get 1. In the other case, you have -1/3, -1/3 plus 2/3, you get 0. So the neutron is electrically neutral, but it still carries this kind of charge, charges of the quarks.
Okay, so we're talking one level smaller than the
Right.
neutrons. That also plays a role. Okay, that makes sense. So if there's 2 of them, is there the antimatter and the matter, you get some sort of explosion potential?
What you would think you create radiation or new particles.
Okay. So if this were to be happening in space, so you also talk about photons, but photons are neither of the 3.
Right, so there are some particles which are their own antiparticles. So they have no conserved quantum number. So that's very neat because you see our lamps, you just can create photons out of the nothing. If there would be a conservation law, you could not do it.
Okay. There's a question in the back.
So the clear results that we detected, or someone detected, that we didn't follow. My question is there any known reason where this antimatter can just be spontaneously formed? I mean, just detecting it doesn't necessarily mean like there's an entire star of it, but maybe it can spontaneously form and have like a really like a collision between 2 particles.
Right, so this is the kind of thing, what I said, this now you require some kind of real calculations. So if you have a collision between the 2 protons and they have enough energy, then you could create antiprotons. I mean, you could have proton, proton, antiproton, proton, then still the sum is 2. That's fine. But then the thing is somehow the more complicated the object is, the less likely it is that you create it. So it's very unlikely that you create an elephant in this way, even if the energy is sufficient. And so this anti-helium-4 is already, it's not really an elephant, but it's already pretty complicated. And so you will, the probability to create it is very, very tiny. Right? So you can create this for particles which would create it, but they normally, they fly away and they don't bind together. And therefore, that's the reason why helium-3 may be, but the more complicated the nuclei is, the less likely.
So if you see multiple of these particles, then that's good. That's it.
I mean, this is always, these guys, they see billions of particles. So the question is, so even if I make an error once per billion, and I misinterpret a charge that is not 2 but 1, you have always some kind of distribution. You are never 100% sure, and you have to understand now your errors extremely well, that you can say with confidence that this is not just a misinterpretation which happens once per big number of attempts. That's a basic thing that In all this kind of particle physics, we have a very rare events, and we have to estimate the probability that you make an error just once every 10 billion times. That's a complicated story.
We have a question.
Oh, we have a question online. Could you give a small look ahead? What are the biggest opportunities antimatter provides regarding measurements of chemical, biochemical decay processes? From Johannes Skidda.
That's a really challenging question. Biochemical decay processes, I would say naively, there's no real, you have this kind of level, physics, chemistry, biochemistry, which is depending on the energy scale. And so I don't see a direct relation.
At least not until we have stars or things that actually hang together.
But then for, the physics for antimatter is the same one, right? So then you would just be on your anti-star, would do your biology, but it would be, everything would be just with antimatter. So this question is more like you mix matter and antimatter, right? And your antimatter just tries to destroy.
Quick question about the helium for discovery thing. Where did they say they discovered this close by to Earth?
Well, so this thing is at the International Space Station, so 300 kilometers above the Earth.
That seems quite contradictory what people are saying. Okay. It seems this discovery or measurement seems very contradictory to what you were saying earlier, where any.
Right, that's what I said. Either it's a revolution,
right?
So you have really to change kind of the standard picture. As a theorist, one has some doubts, because one knows that, how to say, the guy, it's YouTube, so I should not say this, but he's a very famous guy. He's a Nobel Prize winner. But meanwhile, he is 90 or 80, above 85. And at some point, maybe just running in some, okay. Don't want to say anything.
There's a follow-up question. Is it possible to use other particles of antimatter for medical imaging, like the positron emission tomography?
Okay, so that somebody wants to. Yes, exactly. Positron, so. Well, in medical physics, it's true. You use, for example, also antiprotons for this tumor therapy and so on. And so maybe I was too strict. So.
But then, how is it with the stability? Does, for example, an anti-electron have the same stability as the regular electron? So lifespan,
But they are both stable. But if I keep the positron isolated, it will be stable forever.
As long as it doesn't meet their opposite.
Brian, you have a question?
Yeah, I do. When you say photons themselves are their own antiparticles, right? And if I recall correctly, when Paul Dirac sort of made the prediction of what antimatter is, he was speaking that this is a sea of electrons that sort of are inaccessible beyond what would be, if you take time multiplied by speed of causality, you get the distance. So this would be like a fixed point, spatial point. And beyond this is all the sea of electrons or something like this. And this is like a hole would pop out of that, and that would be a positive. Or so is this what antimatter is really? It's just sitting on the other side of this sort of
Well, I'm,
constant volume that's accessible to protons or photons, and then the antimatter particles would jump that little boundary, and they can only do this as small particles. They can't do it with large structures. I'm surprised you say that they do it as
helium.
anti-helium.
But I mean, the first
I
point
wouldn't
is,
believe that they could do it with that much structure.
right, okay, there are two things. The first thing is this Dirac interpretation that there's a C. I mean, maybe you see the problem why he came up to this was, if you look at our formula for the energy, this was E squared is equal to N squared C to the fourth plus D squared C squared. And now we have to take the root if we want to have the energy, right? And this means we have a positive solution and a negative solution. And this gives you this kind of levels that the smallest energy is plus M of the positive energy solution, then I add kinetic energy, and then I have negative energy solution minus M down. So in the kind of naive picture of, I mean, the best at his time, he developed it, was the problem that if I would say there's just an electron, then it could decay to the lower states, decay, and so it could just disappear, emitting energy. So the universe would not be stable. And his solution was to say, oh, let's just say all the states in the negative energy solutions are filled. Then he has this wonderful Pauli principle that says that I can have only one fermion per state, so they are blocked. So this is this kind of picture of the Dirac sea, but unfortunately this is not really the truth, because if you would think the same for, not for an electron, but say for a particle which is not a fermion, then this Pauli principle doesn't save you. So this picture is useful in some applications, but it's not really the correct one. Yeah, so I don't know if I answered the thing, but
Not really.
so they are not jumping. You know, it's not like our particles and antiparticles are jumping in the sea back and forth, but it's
No, it just comes from the fact that, you know, going past what Dirac's original thing, when you start to think of antimatter as time reverse matter, the question is antimatter sitting on some other boundary beyond this photon accessible universe, you know, where massless particles feel no time, right?
that's true.
So there's like a time reversed on one side of what this, and what the universe would be accessible to a photon. I don't know what the universe looks like to a photon, but it looks different to a photon than it does to us, because we have structure. We're a bunch of particles all put together. So my question is like, is the antimatter all sitting on the other side in the reverse time? Or
No.
in the way,
I mean,
it's hard to explain.
it's hard to explain. I mean, okay, if you look back to our picture where I wanted to say that actually there's a region in space-time where we are not sure about the time order. This is the point I said we need special relativity and quantum theory, because this is actually only in the region which is outside of the light cone of a certain point. So this means classically the particle cannot even move from A to B, because it would have to move with the speed of light, which is with a speed which is larger than the speed of light. Right. So this happens only in quantum theory, because in quantum theory you could say, well, very naively, I cannot control, there's an uncertainty principle, and I could travel a larger distance than actually which is allowed. Right. So this is not really true. I'm sorry, but naively you could think that classically I cannot travel faster than the speed of light, but there's a slight extension that I could travel faster than the speed of light, which is allowed by the uncertainty principle. And this makes it possible that I can look also into this reactions and then asking for that we need antiparticles. But all this is, I mean, this is a relatively complicated mathematical formalism, and then we invent this kind of maybe illusions which try to explain things, and if you take them too serious, then you run into problems. In the end, you have to do calculations. This is physics. You have to calculate probabilities that something is happening, and then you invent some picture to explain it to the general public.
It's not always easy. I think we need to soon start wrapping up. There's one more question.
Yeah, if there would be anti-stars, would we see them as normal stars? And would they go backwards in time?
No, I'm sorry, this is the backward in time. This is really... no, this is kind of formal operation which connects solutions for particles with antiparticles. It doesn't mean that for an antiparticle really, you know. So this is really, it's a picture which sometimes gives a kind of a useful clue how you interpret things. But it's not like, yeah, you should not take it too serious, I'm sorry. But, okay, the anti-star, this is what I said, since we see it in photons, and the photons couple to matter and antimatter in the same way, the signal would be exactly the same thing. The only thing you can do is, let us say, the anti-star is moving in the interstellar medium, so still there should be these annihilations. So there should be some glow of high energy photons, and actually some friends, they looked for this and they identified 8 potential anti-stars, which means they are not excluded completely, right? I mean, there's no need to think which is the anti-stars, but you know, people start to, it's funny to come into the newspaper with this kind of stuff. So you look for this.
Thank you so much.
Wait.
Hi, thank you so much again for your talk. I suggest we take a 10-minute break and then we come back for our next speaker, who's going to talk about cybergenetics.
I didn't know, but then I saw it. I would always get stuff. It tastes like sound. It tastes like you're drinking like with the sour lemon. Oh, that's tired. Oh my What do you want? But like I always think really? With 2 years? People I like to What's Sometimes if you're in my friend works at IBM and he quit and they have to pay him for a year. So this is really like you were like well, it was more like so that they would have developed apps that were relevant. Like he worked at AI at IBM and they would keep paying him for like a year and it was the last thing job. So then, yeah, exactly. He was going to be a doctor anyway, so he was like, okay. AI
We're just discussing it.
Him and his boyfriend both had like jobs in IBM. Honestly, like within 5 years after graduating, they were making like $60,000. Both living in Central London. It was crazy. And then yeah, go and there's this thing in the UK now, like it's called fast track. He did a degree in environmental. And then you like fast track to be a GP. So you're like, it's like smaller than a medical degree, and you're normally a GP. Yeah. You can do it. It is
So specific.
Yeah, I think it's different because I'm like, what? I don't know.
I just controls the section. That's what it is. You know, they're recording photos.
Yeah, like it was really Is it okay? Yeah, sure. Is it gonna be now? You need to come to question. You need to come to question. He only said one. He didn't say what is the wrong at the right side of yeah. Oh, okay, then it's fine. Okay. Yeah, the computer. I see. Yeah, but then it's I don't have any other. Oh, that's good. You guys You're on now.
Hello, everyone. We are going to continue with the second speaker of tonight. So I hope you are ready to learn about space exploration and the technology that made this possible. So our next speaker is a researcher at NTNU here in Trondheim, and he's going to talk about space cybernetics, Marius Grote, and yes, about how far can we go, actually. I think I'm going to then let the speaker answer the questions, because we only have one microphone. Yep. So you can keep the microphone, and please, if it's possible, try to repeat the question to the microphone so the people who is joining online can also hear. Okay. Yeah. Thank you and welcome.
There we are.
Yeah, hello, good evening everyone. Thank you for having me. My name is Marius Grote, a PhD candidate at the Department of Engineering Cybernetics at NTNU here locally in Trondheim. So I'm going to talk about space technology, how we want to explore space using cybernetics, robotics, and various technology that I've been working on here at NTNU. So I'll share some experience, but also share my visions and concepts for how I would like to see space being explored. So then I also hope for more questions after that and maybe suggestions. So space is a fascinating place. Always been interested in that since I was a small child. I guess most of you have been that as well since you are here. I guess all of you. It's a really intriguing place that I have indulged in and spent several years studying. Started with a bachelor's and master's in aerospace engineering, and then I ended up here, the PhD candidacy. I was at NASA Ames Research Center for 1.5 years. So I've been all over the place and seeing how concepts and technologies are being developed, both for satellites, rockets, and airplanes. So it's really cool stuff, and you're in the right place being here now. So space, again, the universe, how did we get there? Where do we go? These are type of two questions, mostly how did we get here? But I ask myself, where do we go and how will we get there? So I think, humans are space-faring species. So it's a concept that really stemmed from this century. We started building airplanes and started exploring the skies, but now also after rocket launches starting in the 1920s, we also went to the von Karman line at 100 kilometers altitude, and we saw space. For a long time, we knew that there is things outside in the solar system and beyond, but we couldn't really test it and feel it. So now we have, in the recent years, expanded, developed technology very rapidly. We are seeing everything from small satellite technology, amateur rockets being built that can go up to space. I mean, it's mind-boggling how fast the technology is developing. So, asking ourselves, are we human space-faring species? I mean, we are not. We are built to live on this earth, and that's how evolution brought us here. But can we develop even further by using technology? And technology is the tool, our minds. So without the technology, we really can't showcase ourselves that we are. It's possible to explore other worlds and perhaps settle there. So Elon Musk is very fan of settling on Mars and so on. But, there are some controversies whether that is possible, and even if it will result in death. So we have to be careful and do it reliably and sustainably, because we're talking about human lives, and it's not ethical to send people to die. So robotics and technology, probing for where we want to go first is really the key here, being sure on where we land our feet on. So a ship is always safe at the shore, but that is not what it is built for. I mean, that's also technology. I mean, technology that we build on Earth, it's and for the space, actually for space, it's built on Earth and is built for Earth applications. So many of those things we adapt for space and test it and test it and test it. It fails maybe 100 times out of 200 tests, but again, we find one pass criteria that sends us up to space, and it's really difficult to make things fly. It doesn't fly really in space; it flies in the sky. But yeah, go out and survey out in outer space. It's a harsh environment. Very a lot of radiation, galactic cosmic rays bombard spacecraft and astronauts and ISS and whatnot. So temperatures, they are extreme from hot to very cold. During sunlight, it gets really hot, several hundreds of degrees, and then in the shadow of the Earth, for example, if you're on the back there, then it's minus negative 80 degrees or 100 degrees. So it's a non-forgiving environment, and we have to build a reliable technology to do it sustainably. And yeah, so I'll talk a bit about that by using cybernetics and robotics. So that is my background, but also is these are the tools that we use to explore our neighborhood in the solar system, because ultimately it's our neighborhood, and we need to understand more about ourselves through using this technology. Solar system is us, universe is us, and without the technology that I'm going to talk a bit about, then this is not possible. So you've probably seen this Mars rover Perseverance and the helicopter Ingenuity that just landed a couple of months ago. Really fascinating development that we have been seeing in the past years, since I've been born at least. So space technologies, recent advancements. What is the state-of-the-art technology today, and what are the future prospects? So ultimately, simplicity is the ultimate sophistication. That's from a very nice guy called Leonardo da Vinci that said that. So is that really true, or is spacecraft and space technology that sounds really complex, right? I mean, the more complex, the better. But that's not really true. We want to make it as simple as possible. Without simplicity, you also have less reliability. So we ask ourselves also, is small technology also the ultimate sophistication? Yes, it is, because it's simpler, lower cost, and less complex in the electronics and the physics as well. So I mean, everything is simpler in the small technology. So we are currently now in the age of miniaturization. We have seen a lot of things getting smaller. Now I think your phones are becoming larger again. I don't know why, that's a trend, but yeah, inside of the phone, I mean, there are very, very small microchips and even nanotechnology that has enabled compressing a lot of devices in together in this big phone, or small for whatever you have today. But yeah, we saw it becoming smaller. Cameras are becoming smaller. Drones are becoming smaller. And this results in lower cost, less complexity, and more mass production. So more mass production, that means more competition, driving down the cost even further. So this applies very well to space as well, space technology, small satellites, for example, that weigh less than 100 kilograms in mass. And you have also the category of mini satellites and nano satellites. Mini satellites being less than 50 kilograms and nano satellites less than 10 kilograms. So they were getting really small, and we make use of that. So it's a disrupting technology as well, because you have the large satellites developed by ESA and NASA. They weigh, several tons even. They're big as buses. it takes 10 or 20 years to develop. They're really reliable and really robust. They almost never fail, almost, but sometimes they do. Even the Hubble telescope failed with its reaction wheels, and we had to do some improvisation. So you never test it enough, really. So you can imagine a lot of time and effort and costs spent to making sure it works, but then it doesn't. So there's another philosophy going on in these years. That is also together with launch providers such as SpaceX and Blue Origin. They're also becoming more accessible, lower costs, and they're driving the customer demands further so that we can launch more often and launch more small satellites. So remember, these are less than 100 kilograms. The nano satellites are less than 10 kilograms. And I would say about 70 to 80% is there are nano satellites. Most of them are developed by companies or universities, such as at NTNU. We developed a nano satellite, which is a 20 by 20 by 30 centimeter cube. So it's a 6U CubeSat. So it's a 6 10 by 10 by 10 cubes that we developed there. So it's really small, weighs about 7 kilograms, and it can do a lot of things that just as well as a large satellite can do. So I will talk a bit about that. But ultimately, what is the benefit with small satellites? You send up 1, you send up 2, you send up 3, you send up 4, 5, 6, 7, 8, 9, 10. One of them fails, and you can send up a new one. Just immediately, the same product, you just have replicated the one you have built for maybe 2-3 years, and you have updated maybe some parts of the technology every new year. So you're always up to date, and you do it at lower cost, and you can create the same capabilities as the larger satellites that cost billions of dollars. But with this, maybe you can pay $1 million if you do it right. But you can lower the cost even further, hundreds of thousands of dollars, if you produce several of these replicas of the same thing, but just with small updated devices. Just as your phone, we just upgrade with small microprocessors or cameras that have been available commercially off the shelf through websites. You could just buy them online. Often they indicate they have flight heritage, and that's even better. So we can they're qualified to be integrated in a satellite and sent up. So it's really great times that we live in. The capabilities are even better than the larger satellites if they are in constellation. So I said it was cheaper, and you have more availability, and you also have more reliability, because if one fails, the other one can just take over the role of the one that failed. So they collectively can create better temporal resolution, so they can observe an area more frequently. So if you have a target area you want to look at, for example, the Trondheim fjord outside here, every day, this is not possible with a large satellite. One large satellite can just visit it once a week. But with a small satellite, you can do it every hour. And that's our goal at the NTNU, to actually develop this. And so they can be single purpose, they can be multi-purpose, but single purpose, making it simpler, is really the benefit in this technology. So you can build this in your garage really soon. You can build a CubeSat, your own little CubeSat, and you can label it with your name and whatever you want to do with it. So if you're a bit rich enough, you can, I said hundreds of thousands of dollars. So the cost is not developing the satellite itself, but still is a launch cost. So that is still a problem. There are not enough rockets, and I would say customer demands to lower the cost. But Elon Musk is working on it. So imagine in maybe 10 years, then I think we will see a rapid, significant decrease in cost. So build your own garage if you want to do that. Here's the recipe how to build one. Here's the brain of the satellite, the onboard data handling computer, which often is called a flight computer. It interfaces between the commands that you give them. You can upload just scripts in Linux or Python. I don't know who's familiar with that, but probably some are familiar. And just execute commands in scheduled time, and that is basically the brain. I don't know if you see it very well here. Yeah, here's the OBC stack. There's a small little thing that fits within one U, which was a 10 by 10 by 10 cube. So it's really, really small. And then you have actuators. So if you want to move, you have to include the propulsion units, thrusters such as ion gas, chemical propulsion, using also coal gas or whatever you want to use. But that's expensive. You can use water sprays. You just basically use spray water to propel yourself forward in space. And that's a company in Finland is actually developing this kind of thrusters. And it's really cheap, really affordable, and it's meant to be used by amateurs. So yeah, let's see how this goes. And, you also use reaction wheels to spin around, orient yourself where you want to look at. So if you want a camera, take a picture of your house or whatever, then you have to orient your spacecraft with these wheels. So it spins one way, and Newton's third law says, okay, if there needs to be balancing momentum. So if it's spinning one way, the satellite will spin the other way, but much slower to balance the momentum. Momentum should be zero in space because there are no external forces. Not really, but there are slight external disturbances, but really that's very, very insignificant in short time. And you have magnetic rods that control the spacecraft in the same way. I think Michel explained that a bit. How magnetism is formed. So it also uses the Earth's magnetic field and creates a counter magnetic field to orient the spacecraft. If the satellite has a brain, it needs to sense and perceive and analyze the data. So it has sensors such as sun sensor detecting the sun, Earth horizon sensor to see when it is in the Earth's shadow and when it is in sunlight. Then it knows better its position and its orientation. And also star trackers, gyroscopes that sense the movement. You have that also in your phone. IMU you have in your phone. Magnetometer you have in your phone. It's a compass. So and you believe it or not, these are the same that you use in your phone. You can use that in small satellites. So I don't know, $10, $3-5, you can buy these things and integrate them, and they have flight heritage. They have flown, really cool. A bit more expensive is the radio, maybe data relay. You want to take pictures, you want to catch telemetry data, and you need to transmit that to Earth and to the user, to humans, and to make it understandable. And that is through radio communications. And recent development has also been in optical communication using lasers. That doesn't sound very promising if you want to beam a laser towards Earth, but they are working on it. It doesn't sound very safe, but they're working on it. It's becoming a real thing too. And Wi-Fi, if you have a constellation, as I said, of small satellites, one with the other can communicate with each other if they're within 50-kilometer reach. So if they're very tightly packed, you can also use Wi-Fi, and that is really power efficient, to say at least. And here you can build a satellite that talks, eats, thinks, sees, and feels, and can move itself. So it's basically a robot that you're building. So how you want to move around? If you have enough money and if you want to do it on small satellites or a big satellite, I mean, you can use propulsion methods. And since this is a space talk, I want to talk about this propulsion stuff because it's rocket science. It's really cool, but it's not really used that often for small satellites, at least now. As I said, water is more popular now than using this stuff. So chemical propulsion uses gas, hydrazine, bipropellants. Gas can be, nitrogen, helium, propane. There's a lot of different things that you can use for that. often expensive. Electrical propulsion, you can use electrical field that creates a magnetic field, and then a plasma to propel yourself, often in a spiraling trajectory. So you won't go straight in a line, but you will just spiral, take longer time, but it's more efficient. And then you have Hall effect thrusters, also creates a magnetoplasma, also works a similar fashion. I won't go into details how that works, but maybe you can read about that another time. But the solar electrical, that's also, it takes solar energy directly and propels itself using electrical thrusters. So that's also cool stuff. But my favorite is the solar sailing. So you can see here. This is fuel for free. So it uses the solar radiation pressure that is continuously emitted by the sun. And it can propel itself to infinite distance. So infinite acceleration, infinite distance, if you want to. The infinite distance is going to take a long time, but whatever. This is really cool. And the way it works is that you orient your sail. You can change your reflectivity of the sail to design how your acceleration is going to be and where you want to go. So it's also becoming more popular to look into this and utilizing it for smaller satellites. And another free method is to use a gravity assist by planets and moons. For example, the Voyager 1 and 2 missions, maybe many of you are familiar. We use Jupiter and Saturn to survey also Neptune and Uranus. At least Voyager 2 did that. I'm not sure Voyager 1, I don't think so. But Voyager 2 did that. And that's if you want to go in deep space. No small satellites have done that yet, and I don't foresee that happening very soon, but at least the Moon and Mars are potential candidates that already have been proven to have orbiting small satellites. NASA has stood for many of them, and ESA is now looking into a constellation around the Moon. So they need these propulsion units, whatever that is. Mostly it's ion engines and chemical propulsion, but it's becoming more and more popular. So to propel yourself, move and see around. I talked a bit about that, but if you can click the video, the macro perspective that the small satellites and satellites offer, the bigger ones, it's really important to understand the state of our home, the Earth, to monitor the oceans. Here you can see a phytoplankton bloom through photosynthesis, creating chlorophyll, green light. And it's actually if you extrapolate this idea, you can see the Earth as breathing. So I like to think of Earth as a breathing organism, which, if you're really mystical, then maybe you think that's true. But yeah. I like to think of it as that, and you go to the doctor to check your health. I think having more satellites checking the health of the Earth is more and more important as well, because they are the ones responsible for us understanding that global warming is it's a real thing. So without them, we wouldn't be in the state we are now of understanding. So self-perception, understanding our home, and exploring beyond is two very, very important things for us. So we at NTNU, we grabbed the opportunity to create a mission and actually look at the Earth, look at the oceans. We are interested in seeing how the health of the ocean is, and particularly monitoring the pigments in the ocean that are emitted by phytoplankton blooms in the form of chlorophyll. So to do that, we have installed a hyperspectral imager that sees 400 to 800 nanometers. That is in visual and near infrared range. It has a 5 nanometer spectral resolution, so really high resolution. We can see very fine details in the spatial and spectral domains. RGB camera and your eyes can see only 3: red, green, blue, RGB. So a hyperspectral camera, here you can see here the picture is a real spectrogram of our camera here. can see over 100 spectral bands. So what this enables us to do is to do onboard target detection on the satellite, makes it think, and classification once it sees a signature in the ocean, or if a crop is really in bad state or something like that. I mean, this is part of the mission objectives that is for HIPSO-1. So we hope after the launch that we will understand better about HIPSO-1 and create HIPSO-2, 3, 4, and 5. Maybe we should stop there. I don't know about funding, but yeah, at least HIPSO-1 will show a lot. And yeah, stay tuned in December when it launches with the SpaceX Falcon 9 from Florida, Cape Canaveral. It will be a fun event. And I want to show you now a video of about the mission. We can take maybe a short 15 seconds, 20 seconds break. Or not? I think she's ready. Yeah.
Just a second. We add it to streaming now.
Yeah. How am I on time?
Yeah.
No. We're always over time.
It's okay, you can talk longer.
Okay.
There it should be. There.
Yeah, I'd like to watch this video. It's about HIPSO-1, how it will work.
About 70% of the Earth is covered with water. The great oceans play a central role in our planet's health and climate. The space age gave us a new paradigm in technology. But it wasn't just about exploring the universe. We also discovered ourselves. Today, thousands of satellites orbit the Earth, helping us understand the bigger picture. But to fully see it, you have to think smaller. This is the SmallSat, developed by the Norwegian University of Science and Technology in Trondheim. The SmallSat weighs around 3 kilograms. When comparing this to the huge conventional satellite, it is considerably less expensive to launch and to operate. The SmallSat is equipped with a hyperspectral camera, which register a broader range of wavelengths than the human eye can see. The SmallSat automatically wakes up when it approaches Norway. An algal bloom is drifting toward a fish farm in this Norwegian fjord. The fish farm operator needs to determine if the algae is harmless or deadly for its livestock. SmallSat is requested for assistance. Mission Control transmits target coordinates to SmallSat, as well as deploying an autonomous surface vehicle to collect water samples from the area. When the SmallSat is in position over the fjord, it starts scanning a 50 kilometers wide area according to the coordinates given. The camera scans in horizontal lines and assembles the information into an image. The SmallSat's powerful computer analyzes the hyperspectral image to provide early warnings of harmful algae. At Mission Control, the analysis from the SmallSat is compared to the water samples collected by the autonomous surface vehicle, confirming harmful algae in the scan area. If needed, Mission Control may also deploy an unmanned aerial vehicle as well as an autonomous underwater vehicle to complement the analysis. With this information, the fish farm can now make decisions necessary to avoid damage and loss of stock. When SmallSat leaves Norway, it goes back to sleep to harvest solar energy before it is woken up again, full of energy for its next mission anywhere in the world. We are committed to give the world more effective monitoring systems for climate change and our oceans. It's a matter of going smaller and smarter.
Hallo, vi er Anna og Erika, og vi er studenter her på BI Trondheim.
We got some.
Okay, so it doesn't go to sleep and it doesn't wake up. It's always awake, or else we will lose it. So just for saying that. Yeah, so you can see in the end that it works together with multi-agent robotic system. So it works with the drones, it works with underwater vehicles that are autonomous, and the surface vehicles that are also autonomous. So they are all here in the fjord that are ready to go to action. So they're already in use now and are frequently on field campaigns. So we want to demonstrate that the satellite can provide the macro perspective while also the robotic agents sample and observe the area in finer details. So going from kilometer scale, you can go down to centimeter scale. And that is really applicable to many of the objects in the solar system that we want to look at. But I think, demonstrating it on Earth first is a really good concept. I mean, NASA is already on the way. You saw the rovers, you saw the helicopter. They're working autonomously together as well. But, having the whole symbiosis here and making university students do it, that is our impetus, So we don't have to be NASA to do it.
Ready.
Yeah. So robots, right? So we saw in the end, we had aerial vehicles, underwater, and surface vehicles. So they offer the macro perspective to the micro perspective, as I said, and they have to have independent but dependent operations. They have to talk with each other continuously when there is coverage. So to work autonomously in this sense of ocean color monitoring, the satellite has to directly communicate with the surface vehicle, send target coordinates when there is detection made, and the surface vehicle or unmanned area vehicle will go and investigate further. And that can tell the local fish farms, okay, there is something up here, there is some danger, there is harmful algal blooms. Don't go and swim near it. So these are concepts, that we need to apply elsewhere too. So I'm trying to extrapolate the ideas that we have for this project to other places. So same concepts already are being developed. We are looking at Martian and lunar caves. University of Vigo and also NTNU are looking into how to explore these lunar caves at first with this type of mini rovers that you see here that are being deployed by a bigger rover and then has to execute the mission objectives. And there you can expect a lot of interesting things being under here. It's being sheltered from meteor impacts, radiation. So we don't know what's really in there. And this is a real picture of the moon, of a volcanic cave. This is not the real stuff, but this is in Iceland where it has been demonstrated working a drone. This is a drone, so nothing flies on the moon, but still, this is it's more about the autonomous operations that we can apply to devices like this, spherical robots that can propel themselves in vacuum, near vacuum, and work on their own. So really cool. And we also have sea snake robots. So maybe some of you have already seen this, but they are used for oil and gas services here in Norway, and also for sea exploration. And here we have a very nice thing from NASA that also goes into the deep sea and explores. So thinking how you can use them together with satellites, all the other assets that were mentioned, that is the interesting part. So what are the targets? I talk about what we have available. So Earth is not the cradle of humanity, but mankind cannot stay in the cradle forever. Konstantin Tsiolkovsky, right? So he's also a rocket man, started rockets. So let's start with the moon. The NASA's Artemis program wants to land humans on the moon again, return humans on the moon, on specifically the south and north pole, by mid-2020. So you can see that we're already running a bit late and probably will be delayed, but still, that's going to happen. And the next astronaut, for those who didn't apply yet, there is a possibility of going to the moon. So this is a serious thing. So how to, survey, collect samples. I mean, you will have the architecture of rover, spherical robots that we saw going into the caves, and satellites communicating with the Earth or other assets that are remotely based from humans that also can be on the moon. And eventually, in some decades, we can plant plants in plantations like this. So that is the concept. And the moon can then serve as a base, preliminary base, before we survey other bodies in the solar system. Venus is also one of my interesting places to look at. We can have balloons, we can have really sturdy, robust rovers, and we can have satellites working together, and they need to be autonomous. Underneath the thick cloud and atmosphere of Venus, everything is crushed. Everything, it doesn't communicate. You lose a radio signal. It's really difficult. Venera 9 lander only lasted for 53 minutes when it landed, and took this picture before it died. So you can just imagine the harsh conditions there. 93 Earth atmospheres exist on Venus. So it's not really a place you will find life. Although there have been some speculations that there are some living in the clouds, but I'm very skeptical to that. Yeah, we don't know before we have investigated. So Mars. Some of you wanted me to talk about Mars, so here it is. Hot topic, Mars. We have Perseverance rover, we have Ingenuity helicopter currently, we have the Tianwen-1 from China. And yeah, here is a picture of the Ingenuity helicopter just right before taking off. It's been successful. Here's a concept of the Perseverance landing with retro thrusters. Yeah, and also, if you apply for an astronaut, you might have the chance to go to Mars in your lifetime. So, yeah, this architecture will look like this. You would have all these assets and also potentially have plantations and doing terraforming. I think also Musk was a proponent of that. But, yeah, well, let's see. And back to, I mentioned the sea a bit. Europa is a very interesting place to go to. It's one of Jupiter's moons. And I envision the sea snake robots, the deep sea robots, and satellites just working autonomously and doing operations together without human in the loop. But that's really, really difficult. And but I think some part of our architecture we're developing at NTNU, and some are already working on it, but they just don't talk loud about it, is how to, at NTNU, how they actually want to deploy this type of architecture. And so they have to drill into the thick ice of Europa and then submerge themselves and communicate with some drilled-in Morse or something like that. But that is very, very difficult. But I think we would be surprised what we could find. Maybe we can find volcanic activity, maybe life. We know that life is very, very abundant near warmer regions where you have volcanic springs, underwater geysers. So I think this is a very interesting place to look into. And another moon with a lot of liquid water, not water, methane. It has lakes of methane instead of water. So methane is really interesting because it's also a compound that we find where there is life. And we also find in Titan there's a lot of carbon, organic carbon, that are the fundamental building blocks for life. So also an interesting place to look at. And we can have balloons, satellites, also drones, and we can submerge ourselves in these methane lakes. So stay tuned. There's a lot of research going on this, and yeah, really interesting. And for asteroids, does anyone know what the bright white spot is? No? Have you heard about it? It looks like an alien thing, right? I mean, it's on an asteroid, so suddenly there is one white little bright spot. So it's actually salt. How did salt end up there? We don't know. So people thought they were diamonds. People thought they were, ice crystals, but actually salt. We don't know what's under the crust here. Again, architecture, rovers, satellites, spherical robots. There are probably crevices and holes in it we can dig in under, because this just revealed itself suddenly due to solar radiation pressure. It was warming up, and then the crust fell off into space, to evaporate it. Yeah, we'll also have to drill a bit. Yeah, so as a very nice man said, astrophysicist actually, Carl Sagan. For me, it's far better to grasp the universe as it is really than to persist in delusion, however satisfying and reassuring. So keep this in mind. Don't be thinking inwards, think outwards, and I'll be looking forward to any questions. And you can follow me on Instagram, LinkedIn, Twitter. Facebook is for myself. You can follow me there too. But yeah, I think yeah, I'm open to any questions, and Ad Astra, as I said.
As I said, I think I will use the microphone, and then just link it here to make sure that we see the questions. So we have a question there in the corner.
So when you talked about battery and electronic systems, I, as an electrical engineer student, would be concerned about temperature.
Yep.
Because this satellite would spin. Sometimes it's close to the sun, and sometimes it's over the sun. So
right.
The temperature would be so high and so low.
Right.
So how could you design the batteries and electric systems for very high temperature and very low temperature at the same time?
Yeah, so a funny thing is that, I talked about low-cost things, commercial off-the-shelf products. We actually use lithium-ion batteries, so nothing worse than that. And yeah, it's funny because the satellite itself is very hot and cold on the surfaces. But while it spins around maybe 1.5 hours in orbit, goes from shadow to the sun, it doesn't manage to dissipate all the heat and get too cold within that time period. So inside the satellite is actually more or less 0 to 30 degrees centigrade. So it's very ambient conditions, and just by luck. But if you're further out, if you're about 500 kilometers, 800 kilometers or so, you can get very hot, and then you would have to have cooling management inside the satellite, and that's really expensive. Active cooling. But yeah, you're right. The battery is it is a problem eventually. So small satellites too, as I didn't mention that, but they have a lifetime of about 5 years, and the 5 years is limited by the batteries because they degrade in efficiency, and yeah, the capacity isn't as good after 5 years as it was in the beginning. So they decide it's too much hassle, and they just turn off the satellite, even though it can still live. After 5 years, typically they turn it off.
Could you catch it? Or
The satellite? I guess some are trying to develop concepts on that, but right now, no. It's really small, and it evaporates really in the atmosphere upon the re-entry. So it's a difficult task. You would have to send up another satellite, grab it, and then somehow return it safely to Earth in a capsule or something. But well, yeah, it's already so degraded that why would you do that? You just send up a new one. So the junk basically evaporates in atmosphere, contrary to the large satellites that you need to move into graveyard orbits, so they don't hit someone on ground. Yep. Yep. Next. Yep.
Maybe a related question to your last point, but there's been a lot of concerns about space debris.
Yep.
Satellites.
Yep.
How are the risks of small satellites?
Small satellites are very little risk to the space junk thing, but I think the philosophy behind it is a bigger problem. So companies, they are competition, right? They want to send up as many satellites as possible. You've probably seen Elon Musk with his Starlink satellites, and I don't think that's a very sustainable fashion how that's evolving. There is a space law that is set for everyone that has orbiting satellites. Everyone is responsible for deorbiting less than 25 years. So what that means is that if you're below 800 kilometers, you need to deorbit. You will deorbit yourself, but above 800 kilometers, you have to have some techniques to either put yourself in graveyard orbit or disintegrating yourself. But I think it's a big concern, and I'm not happy with really the trend new space age, everyone joining, and really saturating the orbit, because normally, for example, the orbit we go to with HIPSA-1, 500 kilometers sun-synchronous orbit, it's mostly used by everyone. It's so popular. So it will at some point saturate. And if you collide with another satellite, you just creating bigger problems, because the smaller fragments will collide with other satellites again. You create a chain collision, So I think we need to think more sustainably, and I think we will at some point. The big advocate for this is Maury Bajawa at University of Texas. Know him very well personally. You should look into his research if you're interested, because he's trying to scream about this on CNN, but it seems nobody wants to listen yet. Before it's too late. That's typical human. Yeah.
What is your opinion on the raising interest of sending more and more satellites into space? Like Elon Musk, for example, plans to have I think 10,000 satellites. That's a topic of light pollution as well.
Yeah, it's a pollution problem, and as I said, at some point, even the smaller satellites will re-enter the atmosphere. So what if you have millions of satellites re-entering the atmosphere? Metal, platinum, gold, whatever it is consisting of, it pollutes the atmosphere, and it's not really ethical to not do it more sustainably than we do it now. We put things on the moon, we put things on Mars, it stays there almost forever, and we're not thinking further beyond that. So I think a company has to show it can be sustainable. Why we are so obsessed about it here on Earth, due to global warming, due to pollution of plastic in the ocean and all of that, but then we forget that we also have all of the near Earth space that we need to take care of as well. If we destroy it, there is no reverse. We can't reverse it. So it stays up there forever almost. If it's over 800 kilometers. Yeah.
I think we are left with one or two more questions. Luckily, we have the social network here, so I'm sure Marius will be happy to.
Yeah, I will be happy to answer questions. Yeah.
So, please.
Okay. Thank you. I have two small practical questions.
Yep.
One is when you use small satellites.
Yep.
So you can detect technologies, but you can't actually measure, for example, surface waveforms.
No, not directly, no.
No. Okay. Then the second question. From the video that you showed, it seems like the satellite now runs in commercial mode, like on call if someone needs it. But actually, does it also collect some data that can be shared openly to public?
Yeah, everything will be public. But if the customer or the aquaculture fish farms, they want specific tailored warning signals before we play around and put it public, we'll just give it to them immediately, the raw data.
Right.
So everything will be public. So
okay. So for example, if one of the research group in NTU, they would like to use data to do some research.
Yeah.
They can just contact.
I will just download. Everything will be available online. So
Okay, yeah,
and contact us if you have questions. Yeah, yeah. So definitely, if you have questions, if you want tailored data products, this target detection classification products we use machine learning, for example, on board a satellite. You can get this process data as well. You get just the signatures in specific regions. Yeah, really cool stuff. Yeah. So yeah, thank you. One more question. Yeah.
When do you think will the system be in stable operation?
Hitzel?
Yeah, the one that I do.
Yeah, the satellite only or the whole thing?
Yeah, the whole system, like the satellite with the UAVs.
Yeah, that kind of needs to be verified, demonstrated first, but commissioning mode, that means that you're checking out the subsystem, making sure everything works fine. Yeah, checking with the satellite basically. You do that for several months. It takes several months to make sure it's operationally ready. So December, I would think March, April, it should be ready for operations. And then demonstrating with the multi-agent architecture, it will take a bit while, but our goal is in the summer. Yeah.
Thank you so much.
Thank you.
So we are going to take another 10 minutes break, get some fresh air, and be ready for our last speaker of the night.
Yeah, what?
Because I'm small.
Oh, I can. Yeah, that's so true.
Because sometimes I'm like, check out the latest learning class messages. And I'm like, yeah.
I can say I'd be like, throw one up to me, baby. Or you can
I think we did that Valeretto. What do you need to do?
We want to add this one question from
I didn't remember.
our team. Yeah.
Is it not on the slide?
We try to find out.
Yeah, of course. Of course. Here it is. Thank you so much.
No, I don't. I mean, I'm
It's not there in general.
But what if I send it to London? It's a question. Could she send it? Yeah.
Or else I can disconnect from here. No, I can, or I can send it to one of the questions. Yeah, and you do all the questions, right? Well, yeah, some of them. But if she is online, then she can. Yeah, I'm gonna try.
And then you guys are like answering time. Yeah, so that's how it Yeah, I just sent it to Ronja. We'll see if she can edit it faster.
Send the question to Ronja. Send the question.
Yeah, I sent the question to her. Maybe she can edit because she works with Sectrets. She used I don't can't find the question. But I sent the question to Ronja, so maybe she is against the There was such a big difference between the sound that you use on the microphone and that microphone. I think a lot of times when you guys switch, the speaker was so much sound. Yeah.
I was going to say we're already behind the schedule again. Okay, everyone. Welcome back. So before we move on to our next speaker, as has been said already, we've had a really kind sponsor, the organization Dion, and we've got a representative from Dion here today. So they're going to briefly tell us a bit about Dion, what they are, what they do, and how other people in the room might be able to benefit from their services or funding. So I'll give the word to Sime.
Hi. Thank you very much for organizing. And if you are a PhD, postdoc, and researcher staff in NTNU, it would be nice to give me your attention. So the new board of Dion, which is an interest organization for PhD postdocs and research staff of NTNU. Recently has kicked off, and these are the new board members. We have 2 members from Gjøvik and 6 from Trondheim, and this laughing guy is me. Yeah. So what can Beyond do for you? We are actually a contact point. So you can contact us if you have any inquiry about your work situation, if you are not happy with your supervisor, if you have a problem at your work environment. We can have a contact point. We will forward your email to the right place, and we will support you as far as we can. We will have events, social events and scientific events. And yeah, so we have a specific members who are sitting there waiting for your inquiries. So you can ask us questions and we will answer. And yeah. So Beyond's rule at NTNU is that we are consulting NTNU board members. We are in the National Doctoral Organization. And yeah, so also we are a contact point for labor unions, Techno. And yeah, so we have collaboration also with the NTNU student government. And yeah, so our focus is most into the research employees of NTNU, social integrations and working environment, and also language issues for the international students. We have had some nice events, even last year. We had improv, we had mini golf, ski, happy Easter, and yeah, also maybe a cooking contest. So if you want to join the Dion board, you can do it if you are a PhD and postdoc. So first of all, you have to have yes, a contract with NTNU, and you can do it by joining the annual general meeting, which is held in April or May, and you will get 1 month PhD extension for 1 year to be in the board. So, if you, how many are you in PhD postdocs? Okay, so it doesn't take that much time. Open your Facebook and like our Facebook group, which is dion.ntnu, and you won't regret it. Yeah, that was all. Thank you very much for this nice event, and I hope we can have it more. And yeah, have a nice evening.
Thank you so much, Siamak, and thank you, Dion, for your support. We're very grateful, and we hope to be able to make this event happen more often in the future with your support. So that's really lovely. So our next speaker is Jonas Kjemsland, and he's a PhD candidate in the Department of Physics. And we've learned a bit about antimatter, but now we're going to learn a bit about dark matter, which is also got to do with space. So please give him a warm welcome for Jonas.
Yes, thanks a lot. So what I will do today is, well, I guess be a bit more specific than the last 2 speakers. So we'll talk about a short and small, fun little project me and my supervisor Michael had last year during their lockdown, where we studied so-called reacceleration of charged dark matter. What I basically will do is to tell you one way of learning something about dark matter, which we cannot detect directly without detecting anything. So just the fact that we don't detect it, we can use to learn something about it. See, I will basically split this talk into 4 parts. First, I will discuss dark matter and why we know that dark matter exists, in particular in the Milky Way. Then I will discuss the propagation of charged particles in the Milky Way, and then about turbulence in general. And all these three topics are, well, more or less unrelated. Then at the final end, I will discuss what would happen if the dark matter that surrounds our galaxy has an electric charge. And as a spoiler, what would happen is that it would basically suck up all of the turbulent energy in the magnetic field in the galaxy, and that is obviously not the case. And we can then use this to say that dark matter is not electrically charged, or at least we can use it to limit the possible charge that the dark matter can have. So the animations does not work, unfortunately, but I always have a backup because they never work. So in this plot, you can see the rotation velocity of the galaxy as a function of the galactic radius. So what this basically is how far a star in the galaxy moves around the galactic center as you move away from the galactic center. It's a bit difficult to see, but this solid red line on the top is what we observe. But if we now take our physical laws and look at all of the stars in the galaxy, what we actually expect is something like this dashed dotted line beneath. This is unfortunately one of the worst examples of dark matter in a spiral galaxy, but it's still very local because it's our own Milky Way. So what we actually see here is that this solid line is more or less constant as far as we are able to detect, while what we actually expect from our physical laws and what we observe is this dashed line which falls off with increasing radius. And this tendency actually goes far, far to the right. This is only 20 kiloparsec, but it goes on for about 500 kiloparsec or something. So this small change, or what looks like a small difference in this figure, is actually very significant. And this is then a proof that, first of all, that dark matter exists, but also that dark matter is some kind of matter that surrounds our galaxy in a spherical mass distribution. This is, well, again, not the best proof of dark matter, but still it's the most local one, and also proof that there is dark matter in our galaxy. Exactly what it is, we do not know, because all current evidence and measurements rely on gravitational interactions, but we know little about the nature of dark matter. That is what I'm going to... So today I will show you one way we can learn something about the nature of dark matter indirectly. This is a cross-section, or a picture of the cross-section of the Milky Way. We live approximately here, 10,000 light years from the center of the galactic disk. This is actually, well, I guess not entirely true, because this image is taken from Earth. But imagine that it is a cross-section of the Milky Way. Then we would live approximately here, 10,000 light years from the center of the galaxy. What we can do now is to take this 10,000 light years as a typical distance and a typical travel distance for different particles in the galaxy. If we now, for example, have a supernova explosion or supernova remnant or some other kind of production mechanism for high-energy particles, then we would expect the particle, if they move in a straight line, to take about 10,000 years to reach us, because all elementary particles with high energy moves approximately with the speed of light. However, if we have a look at charged particles, in particular radioactive ions, and measure them, we actually see that the typical time a charged particle moves around in the galaxy before reaching us is not 10,000 years, but rather 1 million years. And that actually means that the particles, in particular the charged particles, has to whistle around in some kind of turbulent magnetic field before reaching us. And now, if we assume that the dark matter that surrounds our galaxy also has an electric charge, then that also has to whistle around in this magnetic turbulent field. So this turbulent field is actually created on large scales, as you can see in this image here. So this is now an image of a turbulent jet where now the turbulence is created on the left-hand side at large scales. And then, at least if you squint your eyes and then make up your mind, then you can see that this large scale irregularity splits up into smaller irregularities, so-called eddies, as we move to the right. So start with some kind of large scale irregularity, which moves to smaller and smaller length scales. Exactly the same happens in the Milky Way. So here we inject turbulence on large scales, for example, due to the mechanical stirring, due to the motion of the galaxy or supernova explosions or something like that, which then propagates to smaller and smaller and smaller length scales before it dissipates. The way we like to visualize this is in the following way. So with this kind of plot, so here we'll plot the wave spectrum or the energy contained in the turbulence as a function of k, which is the inverse of the length scale. So when we start here at around 1, there we inject it, and then it moves to larger and larger and larger scales, which means that it moves to smaller and smaller and smaller length scales. The reason why I'm telling you this is that different particles will interact with different scales. So for example, the proton could interact here, the electron could interact below, and what is important is that if now dark matter has an electric charge, it would typically interact before the protons. So as time progresses, the dark matter would interact before the proton and the electron and basically all particles that we know. One more key ingredient I want to tell you about before we move to the result is the following. This is actually a reacceleration, one of the words of the title. This is basically a word that describes how particles that scatters on a moving irregularity gains energy. And then in a simple picture, we can consider the, the turbulent magnetic field as moving magnetic clouds. Where now, when a particle enters, it whistles around in the cloud and then leaves in a random direction. And then because of the velocity of the cloud itself, the particles will, on average, gain energy. Okay, then let's take a look at the result. Again, animations never works. We have a backup. Here again, you can see on the left-hand side, this wave spectrum and how it evolves in time. So 2 times 10 to the 8 years is approximately 100 times less than the age of the Milky Way. On the right-hand side, you can see the distribution of the dark matter particles as a function of the momentum. What is easier to see in the animation than here is that at some point, approximately around this purple line, so here, you see that suddenly the dark matter particles gain some energy. This is because it now begins to resonate with the turbulent magnetic field. Here we have unfortunately forgotten one key ingredient, and that is that energy is conserved. When it gains energy, it has to take the energy from somewhere, and that somewhere is stored in the turbulent magnetic field. So once we turn that on, the picture is quite different. Then suddenly, the evolution of the turbulent magnetic field suddenly stops and does not continue to evolve, while now the change in the energy of the dark matter particles is not that large. So this is actually a log plot, and we multiply by the momentum cubed. So even though this looks significant, it's actually very, very small and insignificant. So yeah, even today, this change is not large enough so that it can continue downwards. This, even though we only computed up until 10 to the 8 years, it would still be in effect today if dark matter is charged. Then, just for completeness, we could also consider a case where we lower the amount of charged dark matter. And in that case, we can have partial absorption, and that would look something like this. So then you first have some spectrum, suddenly drops, and then continues. However, these effects we do not see anywhere. This is now a plot of the flux of protons and heliums at the location of Earth. Because now this is smooth, it means that all the particles diffuse, basically. If now the wave spectrum suddenly stops, then the evolution of the turbulence stops, and then at some point, some of these particles will then not interact and resonate with the turbulent magnetic fields. And then, basically, just because we do not have a sudden drop in this spectrum, we know that dark matter cannot be charged. Or more specifically, we can use it to limit the possible charge of the dark matter particle. So here I plot the mass of the dark matter particle as a function of its charge. And then, for example, at 10 to the minus 0, which is the same mass approximately as a proton. And you can see that this simple picture, just because we observe that particles diffuse, then we can say that, well, the charge cannot be between 10 to the minus 11 and 10 to the minus 3 electronic charges. And this simple picture is comparable to large experiments such as this xenon 1T experiment that consists of 1 ton of xenon trying to look at the dark matter particle hitting the Earth. So now, just to summarize, what we've done here is to try to learn something about dark matter without observing anything. Just the fact that we don't observe anything, we can use to learn something about the nature of dark matter, because now all experiments and observations rely on its gravitational effect. And what we've seen then is that because all cosmic rays will accelerate when they scatter on moving magnetic irregularities in turbulence, then it will absorb energy, and because there's a lot of dark matter, then it will actually absorb all of it. And this absorption is not observed, and therefore we know that the possible charge of the dark matter is severely limited. That was everything I had, so you're welcome to ask any questions.
Thank you so much, Jonas. That was a really cool talk. I think I already saw a question in the back. No? That question?
Just to clarify for my own sake, when you talk about the charge of dark matter, is this a net charge, or whether any single particle has any charge at all? Can there be like outbalancing charges so that they all cancel, or is it just any charge at all?
Yeah, so in this case, we looked at the charge of single particles. It actually turns out if the charge is large enough that then you can actually make some kind of atoms consisting of dark matter and, for example, dark matter and an ordinary electron. In that case, one could actually screen out the charge. That is not something we consider here. And then in those cases, you should have a charge which is close to unity.
Mr. Chairman, you blow my mind.
Good.
I thought that the whole point we can't see dark matter is because it doesn't interact with electromagnetic. So it would have to have a charge in order to interact with the electromagnetic field.
Yes.
So if it has a charge, then we should be able to see it. It wouldn't be so dark.
Yes, but that is also what you see in this plot, because, let's see. So here we plot it as a function of the, so the Q is now some number times, so the charge is now Q times the electric charge, for example. So in order to have a proton would be up here somewhere. So we do not exclude that. No, not necessarily. You can have an effective charge that is not unity. And in that case, the interaction between the protons would be limited. They could be small enough so that we don't see it. So the easiest way to obtain this is if you have some kind of kinetic mixing between, for example, a new particle, a new photon, in some sense, with a large mass, and you can have some kind of effective coupling to the photon. And that is actually what we observe here, because from the standard model we would expect that the charge is unity. Then we can have new particles with them, which then gives a charge which is effectively less than a unity.
Would you expect, with such low charges, that there would be any phenomena that might, let you see dark matter for a second?
It's
with very low probability.
Yeah, with very low probability, anything is possible, I guess.
Well, with enough observation.
Yeah, sure. So in this case here, as long as you have a charge, you will have at least an effective interaction with the photon, and then you can couple to the photon, and you could observe it at least theoretically at CERN. But then, I mean, when it's too small, then the errors are too large, and you would basically never observe it. At some point, you would never observe it during the lifetime of the universe. They cannot be too small either. So here we're talking about really, really small charges.
Yeah, but you could make it back with the envelope calculation.
What do you mean?
With this small charge, what's the probability that it actually interacts with a photon or an electron?
Yeah, sure.
Yeah.
But I mean, I guess it would be negligible.
Well, negligible in the scale of the universe is.
I mean, the universe has only existed for 30 million years, and then if the probability is too small, then we would never observe it, unfortunately.
Any other question? I have a question.
Yeah, sure.
I wonder, because this is theoretical, so I
Yeah.
assume you simulate those things.
Yeah, so what we did here actually is we solve the equations which I skipped. So all of these plots are solved by, or are found by solving these equations. And this is now a summary of all of these discussions I had. And we can luckily neglect some of the terms, but for example, here you see this W, which is this wave spectrum. And you can see the wave spectrum occurs here. Also when this is this back reaction, this absorption of energy.
What is this wave spectrum again?
This, so this is this reacceleration term. Well, rather this is reacceleration term, which gives dark matter energy, but it has to gain the energy from somewhere, and that is from the wave spectrum.
Yeah.
That is why we have this term here, this growth term.
Mm. But then physically, what kind of software do you use to do those kinds of simulations?
Well,
Do you just do it by
I write them myself.
Yeah.
It's, I mean, it's an equation, you just solve it.
Yeah.
And then hopefully it doesn't take too long.
Yeah. Mm-hmm. Any other questions? One on the back.
More just for my own understanding. If dark matter had a charge to absorb some energy, what would be the physical effect on the galaxy? Is it just that it slows down?
Let's see. So I think the most accurate answer is that the turbulent magnetic field is produced anyways. What would happen is that it absorbs the energy of the turbulent magnetic field because there is so much dark matter. The effect of the dark matter would be small. But then, because this wave spectrum does not go to small enough scales, the ordinary particles such as protons and electrons do not begin to interact with the turbulent magnetic field, and that means that many ordinary particles would then just move straight through the Earth, or at least just through the galaxy, or at least just interact with the homogeneous background magnetic field. That is.
So if I had a telescope,
so this here is measured at AMSO2, which Michael also talked about. What would be the effect is that at somewhere, depending on the mass and charge of the dark matter, you would have a sudden drop here. Because the reason why we actually observe protons from we observe it from all kind of directions, is that they diffuse around and hits us. So what would happen is that at some point, all particles with a energy which is larger than something would then not diffuse and just move straight forward, and then basically no particles would hit us. So therefore we would have a sudden drop here, and this drop is not observed. And because the wave spectrum stops, it absorbs everything, then this is something that we should see by eye.
Do I have another question?
Yeah, sure.
Yeah, so I hear that there's places in space with higher concentration of dark matter and some other places where there's lower concentration. And what's the recent explanation for that?
I mean, they interact gravitational, so we expect it to be where we have a lot of mass, then you would also expect to have a lot of dark matter.
Yeah, I see.
But then I also said that the dark matter surrounds the galaxy. The reason why it surrounds it and is not a part of the disk is that it interacts with ordinary particles. That is also what you see in this plot here. So this green region is excluded because we know that the dark matter surrounds the galaxy and is not a part of the disk only. And then if the charge is large enough, it would interact with ordinary particles and then become a part of the disk.
Yeah. So it seems like it's interacting with itself more than it's interacting with everything else.
Again, it depends on the model, but that is a common assumption because we need to produce it somewhere. And to produce it by interactions with itself is a common assumption.
If there's no further questions, let's give another round of applause. Right, with the final talk, it's now time to get your phones out for some Kahoots. So if you haven't installed
We don't get a break.
Oh, you want to have a break?
It's gotta have a smoke.
Yeah, break, 5 minutes, 10-minute break. 10-minute break and then come back for Kahoot. Make sure you've got Kahoot on your phone so we can start 10 minutes. Yeah.
Yeah.
Want some beer? No, it's okay.
Can I have my phone? Oh yeah, I'll have that. I don't need to be
Yes. I'm gonna get I thought first.
Okay, so we just ran out the numbers of the buskings and movements. Like, you guys something else to say? I think we have another session you thought, which is named Utopia. Okay, you had two. Okay, so 2 plus 3. You also
If you're talking about China, how is
Okay, guys, welcome back. So the Kahoot is up on the screen, and you just need to enter the gate that's behind me on the board to get into the quiz. So it's not just the right answers, it's also speed. You need to answer as soon as you can to get the points. Okay, I think everyone's in. Are we ready to start? Okay, let's do this.
Yes.
True. Tip top in the lead, followed by Vida and Auntie Andreas. More people got this right.
Oh yeah.
Frober in the
Open up,
lead.
baby.
Frober in the lead. Grimy still in third.
I
Tip
can't
top
see
in
very
second
well.
place. Yeah, Brian, grab a chair. Don't look at you.
I'm blind.
Great question. Ooh, we've got a new runner-up, Leah Bruno in the lead. Ooh, Frobro, Grimy, and Leah Bruno on 1 to 1 rating.
How many? Okay. Ooh, how many?
People listen to you.
Yeah.
It's gonna be hard to beat Frobro.
Frobro still in the lead, followed by Grimy. Top race
It's impossible to beat Frobro.
First Space Hotel from Visit Sky.
Who is Frobro? Damn you, Frobro.
Frobo's on fire.
Damn it.
Auntie Andreas,
Never
the
get him.
runner-up.
Never. I had a lot of
Kennedy. Auntie Andreas, you got the second place. Steady. Progress still the lead.
Oh, it's probably perseverance. With curiosity.
Ay!
Woo! Tip top, moving into the top three. Followed by Auntie Andreas with progress still in the lead. There's no points to be scored with these questions. You can be honest.
Wow.
Rude! So rude. That was Brian.
That wasn't
Rip this black. Survive again.
Intereating.
Intereating. Anne was very popular. Please be honest, all the feedback can only be used to improve the next event. Critical comments are very welcome. Just don't be nasty. Don't mind the press and the picture.
Who is this guy? He looks like my whole PhD. very depressed. I didn't like Corona. Yeah, that's a good one.
Yeah.
Earth is not flat.
This is the stock music that comes in.
Supposed to build up. Oh, thank you.
Jim come in third place, Auntie Andres in second, and not very surprising, in the lead, Probro. Where's Provo? Yes! Oh, yeah? Yeah, that's right, Provo. Give Provo an applause. And we apologize for running over time. We did it again. Very sorry. It's really my fault. We're supposed to finish at 8. It's like an hour and a half late. But thanks for sticking around. We're really excited to see so many people here tonight, and we really hope that next year we can make this happen in a bigger space with even more people. So please spread the word, and we look forward to seeing you next year. And please feel free to stick around for more beer and pizza or whatever you like. And thank you to Alicia, Letra, Sophie, and our lovely DJ Artenik for the organization of this event. Like, they put in so much effort over the past months. It's incredible, and especially Artenik making this happen. With the digital part, like, we would not have been able to do it without her. So can I have a wide round of applause? And for Ronja, who cannot be with us because she's in quarantine, but we know you're watching. You're awesome. We miss you. Mwah. And we've got a little video for you to wrap things up. Woo! Okay, that was the end. So you can go back to your beer. Yeah, let's go. I'm gonna go.
Great job. Do you have your backpack? I can still take it.
It's here.
Oh, you have.
Okay.